Hello? Good evening, ladies and gentlemen. Welcome. My name is Peter Chung. I'm a professor in Department of Electrical Engineering and in Dyson School of Design Engineering. The reason why I'm out here is because I'm responsible for organizing this memorial lecture. Before I introduce our speaker, Professor Claudia de Ram, I want to say a few words about Peter Lindsay, who bears the name of this successful series of lecture, because most of you don't know who he is. Peter Lindsay was a professor in King's College, London. He was also an alumni of Imperial College when he studied electrical engineering at the City and Guild College, which was the engineering faculty of Imperial back in those days, a long time ago. The reason for this lecture series was that he left in his will the entirety of his estate to the Old Centralian Trust, the charity branch of City and Guild Associations, to support the engineering students' activity at Imperial College. He didn't leave any to the King's College. I hope none of you here is from King's. But too bad, I can't do anything about that. This bequest contributes to a significant proportion of the trust's available fund to support students. There's a condition in the will that the EE department will organize an annual lecture under his name. Well, here's a lesson for all of you. If you want to be remembered, this is one way of doing it. Giving us lots of money to engineering. Now back to this evening's lecture. I forgot to advance this. This is Peter Lindsay. Back to this evening's lecture. I'm delighted to introduce to you Professor Claudia de Ram. Claudia is currently a professor in theoretical physics here at Imperial College. And she's doing teaching, research, and so on. And yesterday when I saw her, she actually had exam scripts that she was marking on her desk. You can find out from the brochure in front of you on the table her impressive academic credential. So I'm not going to repeat it here. Yesterday, I met up with her in her office. I asked her to tell me something interesting about her so that I can introduce her here. And in her modesty, she only told me that she's Swiss, and she's related to a famous mathematician called Georges de Rome. Not being a mathematician, I didn't know who that person was. In reality, she's far more interesting and exciting. From the inside jacket of this book over here, this is the book, The Beauty of Falling, and she published that last year. I discovered that Claudia is not only a physicist interested in gravity, cosmology, and theoretical physics, she's also a diver in the ocean. She is a pilot, I assume it's airplanes, and an aspiring astronaut. That was a surprise. She also once worked at Jet Propulsion Laboratory on gravity on Mars, and as a student there. And her adventure in physics took her to France, from Switzerland to France, to Cambridge, where she got her PhD, then worked in Canada, United States, and for the past 9 years here at Imperial College. She is well recognized as an exciting speaker who can explain complicated ideas in physics to other lesser mortal like myself as engineers so that we can understand it. So may I invite Professor Claudia de Rum to come up here and deliver for us the 17th Peter Lindsay Memorial Lecture.
Thank you. Thank you, Peter. Thanks. Thanks, everyone. It's really, really nice to be here to celebrate Peter Lindsay and his will. And I'd like to thank Peter Chung for organizing all of this event. So it's really a huge honor to be there. I'm Claudia de Rum. I'm a member of the Theoretical Physics Abdus Salam Center. And our job as theoretical physicists is to come up to build models to describe the universe all around us as accurately as possible and to come up with predictions. And so in spirit, in fact, the models that we build, they're not so dissimilar to the devices that are engineered in electronics or even some of the instruments that have been built in space exploration in other parts of Imperial. The models that we have, they of course have to be accurate. We need to be able to rely on them. They need to be efficient. But a lot of them, we need to be able to use them, to push them into the most extreme environments. And so just like some of the instruments that are being used and built here at Imperial are being sent to the edges of the solar system, in fact, the models that we build, they are being pushed to the edges of the observable universe. They are being pushed to the edges of space-time itself, whatever that is. And so to ensure that the models that we have or the device that we engineer make sense and are stable in the most extreme conditions, we rely often on symmetries, which create some balance and allows us to have some stable models. And so that's why in nature, but also ubiquitous to all civilizations, in arts and in engineering, but also in the laws of physics, we rely very strongly on the notion of symmetries. And in fact, that's probably why we have developed to be attracted to the notion of symmetry, because it creates some kind of balance, it creates some stability that we're eager to have. But in nature, just like in art and just like in the laws of physics, sometimes we come across some situations where the models break ever so slightly, very subtly, the symmetries. And rather than thinking of this as an imperfection, as a failure of our models, at least my research is built in using this as an opportunity for discovering something new that goes beyond the original symmetries. So, of course, we can't do whatever we want. And so if we start with, let's say this is a model, which at face value has no symmetry whatsoever, it doesn't have any structure that we can necessarily rely on, we see that the balance doesn't work and it simply falls apart. But in some situations, some of the models that we look at, they may not appear as appealing from the outside, but we can engineer their internal structure. In here, for this teapot, we can engineer the internal distributions of masses so that the balance is satisfied. There's an internal symmetry in disguise that enables for the system to be stable. So what I'm trying to say is not that our universe is modeled like a big spinning teapot, although sometimes it does feel a little bit like that, but rather that our job as physicists is to rely on symmetries to describe the laws of nature and to describe the laws of the universe. And in fact, if we look at the universe, it is governed by one of the most powerful and one of the most exciting phenomena that there is, which is gravity. So we're all very familiar with the gravitational attraction. We were all very familiar with gravity here on Earth. And in fact, gravity, as described by Einstein's theory of general relativity, is the most precise phenomenon that we have at our disposal at the moment. In fact, we understand the phenomenon of gravity so well that we can describe the motion of the moon around the Earth within a millimeter precision. And we understand this so well that if we wanted to be better in our modeling of the motion of the moon around the Earth, we would need to account for leaves growing on one side of the hemisphere in the spring, like now, while they fall down on the other side of the hemisphere, and that changes ever so slightly the balance of the distributions of masses around the Earth, and that changes ever so slightly the gravitational attraction of the moon to the Earth, and that changes ever so slightly the motion of the moon around the Earth. So we understand gravity extremely well, and we're very familiar with it here on Earth, but in fact, when we're describing gravity on Earth, we're often distracted by all sorts of different other phenomena, like the fact that we need to breathe, and the fact that we need to stand on some soil. And so to really experiencing gravity more freely, it's useful sometimes to extract ourselves to all of the distractions that we have in our everyday life. So let's just imagine that we're going to go in outer space. Let's just imagine you're orbiting the Earth in outer space. So this is my dream of becoming an astronaut. Just imagine you are there, and you are falling so freely that you're not feeling anything at all. And yet you're still experiencing gravity, but you don't feel anything at all because your cells, the cells in your body, are all behaving exactly the same way under the gravitational influence. Every single particle in every single atom, in every single cell of your body is experiencing gravity in exactly the same way, and so they're not pushed or torn apart. In fact, there's never such a thing as any buds in a body that can hear or smell or taste gravity. And this is something very profound about gravity. This is a symmetry related to gravity, which we call the equivalence principle, and that was in fact first articulated by Galileo over 400 years ago. Now, we understand this equivalence principle as dictated by Galileo, introduced by Galileo, but I think it's very nice to see it more recently on the moon. So this is a picture of astronaut David Scott during the Apollo 15 mission. And the quality right here of this picture is not amazing, but I'm going to press play in a second, and hopefully it's going to get a little clearer. And when I press play, I'd like you to notice two things. The first one, as you will come with no surprise, is a test of the equivalence principle. So the astronaut David Scott will be holding a hammer on one hand and a feather on the other. He will drop them, and hopefully they'll hit the ground at the same time. But the second thing I really want you to notice is just how excited he is. And just imagine that. Just imagine, it's 1971. He is the 7th human being to step foot on the moon. He's the first person to ever drive on the moon. And rather than broadcasting that to put it on social medias or to plant a flag, what he's really the most excited about is simply to test the fundamental laws of nature. So that's a lesson for all of us. Okay, let's see if that works out.
We'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
How about that?
Mr. Galileo was correct in his findings. We'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
How about that? And you know, I've seen this video maybe 100 times, and it works really every time. It's incredible. So it's really this equivalence, this perfect symmetry, which by now has been tested within 15 orders of magnitude, that is built into understanding of gravity. It's a universality so perfect that pushed Einstein to understand that if everyone is experiencing gravity in exactly the same way, the phenomenon about gravity can't be about the masses per se. They can't be encoded in us as objects per se. The information about gravity must be deeper than all of us together. The information about gravity has to be encoded in the very fabric of space and time together. So you've probably seen such a picture before. We now, thanks for more than 100 years, understand, thanks to Einstein, that the objects like planets and masses like the Earth, but not only masses, anything in fact, curves the very fabric of space and time around themselves. And we're all living on that space-time. We're all experiencing this curvature, and that's how we're all experiencing the gravitational attraction. And in fact, throughout the universe, everything and everyone is connected through this fabric of space-time. And therefore, everything and everyone is connected through gravity. There's never such a thing as gravity at any single one point. The very notion of curvature, and therefore the very notion of gravity, relies connections between different people together, between different points in space and time together. Now, in describing gravity as the curvature of space-time, we often emphasize about the differences between gravity and the other fundamental forces of nature. Sometimes you may hear that we go as far as saying that gravity is not a force and it has to be treated differently. But in fact, for a lot of the phenomenon and for understanding gravity at a fundamental level, it's actually useful to draw a parallel between gravity and the other fundamental forces of nature. And perhaps one of the other fundamental forces of nature that we understand very well, in fact, people here understand very well, is electromagnetism. And for instance, we understand that we can create electromagnetic waves, we can create light by shaking around some charges with respect to electromagnetism. That's how we can create light. And so in fact, exactly the same thing happens for gravity. There's a direct analog to that. I can shake anything which is charged with respect to gravity, but we said that anything and everyone is connected to gravity. So in fact, I can shake anything at all I want. It doesn't even need to have a mass. But let's imagine I can shake a little massive object. And if I try, in fact, to do the same thing as I did for electromagnetism, that wouldn't be very interesting. That wouldn't do anything at all. It's a little bit more subtle. I need to consider some shaking in more than one direction, a little bit like this. And that's why, for instance, if I have two objects, two masses, my two hands, for instance, shaking around each other just like that, they will, they don't. Well, typically they do. Here they do. They shake the very structure of space-time. They shake the fabric of space-time around themselves. That creates waves of gravity, which we will call gravitational waves. And those gravitational waves, they travel through space at the speed of light, just like the electromagnetic waves. Now, it's the year of quantum, so you all know that, of course, that while it's useful to describe light or the electromagnetic wave as a wave, fundamentally is carried by a quantum of energy, which we call the photon. So if I take light of a particular color, of a particular frequency, and I were to dim it down as much as I could, I would see that that light is carried by a discrete amount of energy, which we call the photon. And we know, for instance, that electrons can emit or absorb photons, single photons, when they change energy levels around the atoms. And so all of this picture, in fact, works precisely in the same way for gravity. In the very same way that we can describe gravity as gravitational waves, if we took the gravitational waves that have, in fact, been detected here on Earth in 2015, announced in 2016, and we were able to dim them down, we should see that fundamentally they are carried by finite discrete quanta of energy, which we call the graviton. We probably will never detect a graviton, or it will be very challenging directly. This is just a cartoon picture. Maybe that's a better representation of what a graviton would look like. But our inability to directly detect one because it's so weak doesn't mean that it doesn't exist. And in fact, in principle, when electrons change energy levels around the atoms, every so often they may emit or absorb a single graviton. But the probability for this to happen is very weak because gravity is the weakest force there is. And we're only experiencing it so much in here on Earth because we have such a big mass of the Earth in here. Now, gravity and the electromagnetic force are just two of the fundamental forces of nature, probably the ones we are the most familiar with. But there is, in fact, as far as we know, at least four fundamental forces of nature. So in addition to those two, there is the weak force, which is responsible for the structure within the atoms, and the strong force, which is responsible for the structure within the neutrons and the protons within the nuclei of the atoms. And something quite remarkable is that we think that all of those fundamental forces are unified into one big framework. In fact, we already know, thanks to the work of Maxwell, that the electric force and the magnetic force are not two disconnected phenomena. they're in fact related to one another. And what an observer may perceive as an electric field, for another observer, they may perceive that as well as a magnetic field. So they're just two representations of a unified framework. Now we know as well, thanks to the work of Weinberg, Salam, and Glashow, that the weak force can also be unified with electromagnetism within a framework, a unified framework called the electroweak theory. And so in the electroweak theory, we understand that the weak force is also a fundamental force, and just like electromagnetism, it's also carried by a fundamental particle. But in this case, the name is not very interesting. They are called the W and the Z bosons. Now, the weak force is very important. We wouldn't be here without the weak force. It's responsible for fusion in the sun, so it's essential for life in some sense. It has some applications, for medical applications, for instance. But we typically are not as familiar with the weak force as we are for the electromagnetic force, because the weak force is weak. And the reason the weak force is weak is because the particles that carry that force, the W and the Z boson, are massive particles, not in the sense that they're ginormous particles, but in the sense that they carry an inertial mass which affects their dynamics. And in fact, we understand nowadays, we all understand nowadays, that the Higgs mechanism is responsible for weakening the weak force. It's responsible for the weakness of the weak force. In fact, when we look at electromagnetism, there is a level of symmetry. Electromagnetism enjoys some level of symmetry, which is not obvious from the outset, but it's an internal symmetry of the system. So for instance, if I think of the electric force, and I look at it at how its strength at a distance, while it decreases at a distance, there's a conserved element, which is the amount of the force multiplied by the area. So there's a conservation element in the electric force, in electromagnetism, just like when I think of light and how it shines, the intensity of light integrated over the surface will remain constant. There's a symmetry there which is built into the theory of electromagnetism. And that's not the case for the weak force. The weak force, that level of constancy is no longer there. The weak force, there comes a point where it simply switches off and it does no longer operate. So this breaking of symmetry needs to rely on a stable mechanism, and nowadays we understand how the Higgs mechanism plays a crucial role in breaking the symmetry that comes in for the weak force in a stable way, in a consistent way, and in the same process giving the W and the Z bosons a mass. In fact, you probably know, Peter Higgs very sadly passed away just over a year ago. So I thought it would be a nice tribute to show this. I think it's a lovely picture of him as he was visiting Imperial just a few years ago and interacting, in fact, with our students and postdocs. And I think it's quite representative of how having a Higgs in the room changes the dynamics of everybody in there. So we call it the Higgs mechanism, and I'll continue calling it the Higgs mechanism, but in fact we should call it the Brout, Englert, Hagen, Higgs, Golnick, and Kibble mechanism, because they all really contributed to it. And in fact, Kibble, who was also here at Imperial, also working with Salam, played an essential role in understanding how the Higgs mechanism enabled to have a consistent symmetry breaking. So he really played a crucial role in understanding of those phenomena. One thing which is very interesting for me, for aspects that I'll talk about later, is that the Higgs mechanism, or how the discovery of the Higgs and how the Higgs mechanism works, tells us something essential about how we think of empty space. Do you think of empty space often? If you think of empty space, you may think of something in the absence of anything at all. But in fact, the discovery of the Higgs and how the Higgs mechanism works tells us that our notion of vacuum, our notion of emptiness, our notion of the absence of any tangible particle or anything at all is actually not completely denuded of energy. We know that the vacuum, the best empty space possible, better than in outer space even, is never completely empty. it is filled at the very least with a coherent path of the Higgs, which we know gives a mass to the sum of the other particles. And so that tells us something essential about how to think of nothingness. Now, as you probably know, the Higgs boson was discovered at the Large Hadron Collider at CERN and announced in 2012. It was discovered by scattering particles together, by scattering protons together. And as you probably know, when we do such an experiment, the outcome is never certain. When we scatter particles together, all we can be sure of is the probability, in fact, the quantum probability of a particular outcome. But every time we do the experiment, we don't know precisely what will happen. Sometimes the particles may decide to transform themselves into something quite different. And we understand that very well, and that's why it has been used to prove the existence of the Higgs boson and all of the standard model of particle physics. Now, I can do the same thing with gravity, in fact. I can think of scattering particles, including the fact that there is a curved background around us, that gravity is present, and I can compute the outcome. There may be even some situations, every so often, not very often, but every so often, when a scattered particle, one of them decides to change itself into a graviton. That could happen, and there's absolutely nothing wrong with that. We can trust our theory of gravity associated with the laws of quantum probability to compute the outcome of such processes. However, something we know as well is if I'm trying to look at the same kind of experiment and I built in an energy, I look at energy transfer which goes higher and higher, there comes a point where the outcome predicted by Einstein's theory of general relativity simply stops making sense. There is a point that we don't even need to access with our experiments or with our observations, where we know that the laws of physics that we have currently stop making sense. And this, in fact, is one of the best qualities of Einstein's theory of general relativity, that it predicts its own failure. That's the best quality a theory can ever have, because not only it tells us where to use it and how to use it and how to make predictions, but it also tells us where to look for new discoveries, where there's a new layer of physics to look for. And that's precisely what Einstein's theory of general relativity tells us. Now, the energy transfer at which the theory of general relativity associated with the laws of quantum probability breakdown is relatively large. It's about 15 orders of magnitude larger than what is currently being probed at the Large Hadron Collider. So we're still quite safe. But in physics, we're used to transferring the notion of energy with that of mass. This is the famous E equals mc squared formula that you all know since birth. And we've seen that from Einstein's theory of general relativity, the notion of mass can be related to the notion of curvature. So really what this tells us is that Einstein's theory of general relativity predicts its own failure in regions of the universe where the curvature is too high. Now, in the solar system, the energy associated with the curvature of space-time is always about 50 orders of magnitude smaller than the Planck scale. So it's a very, very safe place for us to be, and we can stay here for a little while. But there are regions in the universe where the masses involved are so high and they are confined in such small region of space that they create some elements where our theory of relativity, Einstein's theory of relativity, breaks down. For instance, for black holes. And black holes are not just theoretical predictions of general relativity. In fact, they are unavoidable in Einstein's theory of general relativity. But in the past 10 years, there's been more and more observational evidence for the existence of black holes. So for instance, on the left here, there are observations from the Keck Observatory, which have been tracking the motion of stars at the very center of our galaxy over a period of 18 years. So every blob here, colored blob on the left-hand side, is a star, and you see that they all seem to be orbiting an invisible mass at the center of the galaxy. And this invisible mass has all the characteristics of what we would expect a black hole to be. And so you can zoom even further in that very same region at the center of our galaxy. And on the right, there are the observation from the Event Horizon Telescope, observing light in the radio frequency. So these are fake colors, it's not visible light. But what one can see is the light from objects located behind that mass being deflected by the gravitational pull of that mass. And that's completely consistent with how we would have expected a black hole to gravitationally lens light around it. So there's extremely strong evidences, both theoretically and observationally, that black holes do exist, and we do think there's one at the very center of a galaxy. So you may have to, this so just decide, you got fed up with everything and jump into a black hole, for instance, the one at the center of the galaxy. This is not what you will see. You wouldn't see blue at all. What you would see actually would be quite pretty, because as you go closer and closer to the black hole, all of the light will become what seems to you of higher and higher frequency. And so the light from the cosmic and microwave background from the very beginning of the universe is not visible to us at the moment, but as you go very close to the black hole, actually the light from the cosmic microwave background will reach the visible range, and you'll be able to see with your own eyes the very beginning of the universe. Unfortunately, that's probably one of the last things that you'll ever see. As you probably know, as you get close to what we call the horizon or the surface of a black hole, you reach a point where the gravitational pull is so high that you can no longer escape. And so that's the end of you. However, as you go, I think you'll be very reassured with the knowledge that for us as theorists, this is a very, very safe place as far as Einstein's theory of general relativity is concerned. We can very much trust our theory of gravity as we cross the surface of the black hole, as we cross the horizon of the black hole, because the curvature involved at the horizon of the black hole, and even as you enter the black hole, are still many, many, many orders of magnitude below the Planck scale. And so we can really tell you what happens to you, lucky for you. And what we know will happen is that you'll be inexorably pulled towards the center of the black hole, where the curvature increases and increases. In fact, we even know that as you enter the black hole, the notion of time and the radial notion of space switch around, and so we shouldn't ask ourselves where the center of the black hole. The center of the black hole is some time, and that's going to be quite quick. It'll take about a few seconds to reach the center of the black hole. But what's quite remarkable is we can use Einstein's theory of general relativity to predict what happens inside the black hole, and it tells us itself that you will be pushed to the center of the black hole where the curvature is becoming so and so and so high that ultimately it reaches the Planck scale where you can no longer use Einstein's theory of general relativity. It does predict its own failure. Precisely what happens at the very center of the black hole, we don't know. Whether that question even makes sense, we don't entirely know. And in fact, understanding the nature of reality, the nature of space and time, as you get close enough to the center of the black hole, is not just an academic question, because the environment there, the level of curvature involved there, is very similar to what happens at the very beginning of the universe. Of course, this is just an artistic view of the black hole singularity, where Einstein's theory breaks down in here, as you get close to the center of the black hole. But this is very similar to what happens if you go back in time in our cosmic history, and as you do so, the curvature increases and increases to the point where it's so high that we can no longer trust what happens there. We can call this a Big Bang singularity, but in fact it's just hiding a lack of knowledge of precisely where we all come from. So understanding the nature of reality at the very center of a black hole is actually telling us we're after the nature of reality of space and time. We're after our origin, the origin of space and time, the origin of the universe, and the origin of everything that is built into. So this is the current picture that we have at the moment. And in fact, this is not really fair. General relativity is not just a good description of gravity. That's not making justice to it. General relativity is the best tested theory there ever was. It's been tested with impeccable agreement on the widest variety of scales that you can imagine. It is the best model that we have for the description of reality all around us. And yet we know that there comes a point where we interrogate it and it gives us answers that no longer make sense. Precisely what happens when we're trying to resolve those singularities, we don't know. There are people in here at Imperial working on string theory. Some other people are working on causal sets. Some other people are working on loop quantum gravity. Some other people are working on yet different models. It's not for sure, we don't have an answer, definite answer for sure, but all of those formulations are really after a more fundamental symmetry underlying the structure of reality. And so for some of those models, like for string theory, it may give us the impression that at face value, we're complicating things out. Instead of describing particles as point-like objects, we're describing them as strings, which may seem more complicated, but this enables us to access a deeper layer of symmetry, which lives in the world of the string itself. And this only happens if we're actually considering a particle which is extended into one-dimensional space and one dimension of time. And that's why we're considering string theory and not, let's say, bubble theory or ball theory or anything more complicated. Because considering string theory is really what enables us to reach a higher level of symmetry, which we can call conformal symmetry, and in fact relates physics at different scales with one another. In fact, it gives us some constraints on how some of the properties of physics at very small distance scales are related to some properties of physics at very high distance scales. And as a cosmologist, this is precisely what I'm interested in. I'm actually interested in understanding how the infinitely small is ultimately connected to the infinitely large through our cosmological framework. And so for that, let's go into the largest possible scales in the universe. We can zoom out of the solar system. We can zoom out of a galaxy. This is an animation that's going to take us out of a local cluster of galaxy, over distances that span over thousands of millions of trillions of kilometers. We can zoom out to those distances, and it would take us millions of years to get there if we were able to travel at the speed of light, which I can't, maybe you can. And what we see on those distances is that the clusters of galaxies in which we live in are embedded in filaments of dark matter, which are represented here in blue, but that's just, once again, fake colors. It would be very boring if it wasn't in fake colors. We don't interact with dark matter, so we can't see dark matter. But in fact, dark matter is a quite conservative element. There's nothing too extravagant about the existence of dark matter, and we understand very well how dark matter behaves. Dark matter behaves like matter. In fact, we often emphasize on the mysterious aspect of dark matter, which is the fact that there's another sector of matter out there with which we don't interact, or only interact gravitationally, or interact very weakly. But the fact that there should be another sector out there of matter is in itself not a big surprise. It's something that we should have expected. However, some of the surprises that we see on those scales is that the further away we look, for instance, at different objects, the faster they seem to be moving away from us. And this doesn't mean that there's something specific about where we are in the universe, but rather means that we are living in an expanding universe. In fact, the objects themselves are not the ones moving. What is happening is that space is being stretched. And so if you look at an object very far away, there's more space between you and that other object. So there's more stretching of space, and therefore that object seems to be moving away from us faster. And this is what's been seen in a symmetric way in all directions everywhere. But now, one thing we know about gravity is that it's an attractive force. And so if the picture I showed before, where it looked like all of the energy present in the universe is confined in the local clusters of galaxies and the filaments of dark matter, we would have expected the gravitational attraction between those filaments of dark matter and clusters of galaxy to make this expansion slow down. And it could even have come a point where the expansion of the universe had slowed down so much that it would have reverted, and the universe would have started contracting to itself, and possibly to a big crunch singularity. And that's the end of everything, just like it was the beginning of everything. That's what we would have expected if the previous picture was correct. But in fact, in the past 25 years or so, it's been shown that the expansion of the universe is not slowing down, it's going faster and faster. The expansion of the universe is going at an accelerated rate. And in fact, there's not just one observation that tells us that. Nowadays, the biggest wealth of information from all sorts of different systems that all tell us exactly the same thing. We can interrogate the light from the very beginning of the universe, which we call the cosmic microwave background, the light from very early on. We can look at the distribution of galaxies in the universe. We can look at explosions of stars and how the light they emit to us get redshifted as a function of distance. We can look at gravitational lensing. And nowadays, we can even use gravitational waves to better understand the evolution of the universe. And all of these systems, relying on very different physics, relying on very different times in our cosmic history, all converge to the same region, all converge to the same information that tells us that the universe is expanding at an accelerated rate. And so, once again, this is contrary to what we would have expected if this picture was the end of it, and if all the energy present in the universe was indeed confined in these dark matter filaments and the clusters of galaxies. So to see if that's really the case, we can zoom into a completely empty region of the universe. There are regions in here, and in fact that's what makes most of the universe, which are completely empty. We call them cosmic voids. Those cosmic voids are millions of kilometers apart. Sorry, those cosmic voids are millions of light years apart. So imagine how lonely you'd be in the middle of those cosmic voids. There's absolutely nothing in there. There's no dust, there's no light, there's no planets, there's no comets, there's no dark matter. There's not even a black hole for you to dive into and get yourself entertained for a few seconds. It would take you millions of years to communicate with the closest star on the edge of the cosmic void. Just imagine how lonely you would be there. And yet you wouldn't be completely alone, because even the best vacuum there is still filled with energy. We know that even in the best vacuum, we're filled with a quantum sea of energy, which carries energy and for the Higgs has an effect on all the particles. We know that for the Higgs, and we believe nowadays that all of the particles that we know exist should give a contribution to the vacuum. This is a quantum vacuum which should have an effect on gravity. So we can interrogate the effect of the quantum vacuum on gravity. And the first thing we need to notice that the effect the quantum vacuum, the energy of the quantum vacuum will have on gravity, is not exactly according to this picture. And that's because this picture just relies on having a mass which is localized somewhere in space. And so that only curves the fabric of space-time around that neighborhood, and we understand that. But for this quantum vacuum that carries energy, it fills every pocket of the universe, from the middle of the cosmic void to the presence of structure. Everywhere in the universe, it constantly fills every element, and not only in space, but also in time. This is a constant of cosmological nature. This is something we can call a cosmological constant. And in fact, the fact that the quantum vacuum behaves as a cosmological constant, which was first introduced by Einstein, is something very uncontroversial and has already been explored over 100 years ago almost. In fact, if we take Einstein's theory of general relativity and we add this quantum vacuum to it, the effect it has on the structure of the universe is to lead to an accelerated expansion of the universe. This has been known for almost a century. The only issue is that the expected rate of acceleration of the universe is way too large. And it's not way too large by a factor of 2 or 2 pi or something we can forgive ourselves. It's too fast by at least 28 orders of magnitude. And that's being conservative. This is the biggest discrepancy in the whole history of humanity. And so faced with this biggest embarrassment, the approach has typically been to ignore the symmetry, ignore the elephant in the room, postulate that for a symmetry or another, for a reason or another that we don't quite yet understand, this quantum vacuum energy simply has no effect on gravity. And then we need to still explain the accelerated expansion of the universe. So I'm just going to pull out of my back pocket a new kind of energy, which I'm going to call dark energy for lack of a better name. And ta-da, that leads to an accelerated expansion of the universe. So there's nothing wrong with that approach. We can always do that. Only it doesn't really address the problem at its core. So what I'd like to do for the last few minutes or so is go back to the original problem and just take what we know should be at our disposal, which is the existence of a very large quantum vacuum energy, and try to use this to explain the fact that the universe expansion is accelerating. So for that, I need to find a way to reduce the effect of this very large quantum vacuum energy on the evolution of the universe and on the rate of acceleration of the universe. Now, in Einstein's theory of general relativity, gravity, just like electromagnetism, has an infinite reach. And in Einstein's theory of general relativity, this is coming from this universality, which is at the core, which is one of the pillars of Einstein's theory of general relativity. And so that tells us that if we consider two galaxies located on the other side of the observable universe from one another, which are located 10,000 million trillion kilometers away from one another, to really fully understand their dynamics, I need to account for all of the quantum vacuum energy which fills all of the universe in between. But not just in one direction. I need to do that in all directions of space, but even more importantly, in the direction of time as well, since the very beginning of time. And maybe this is just too much to ask. Could it be that the underlying symmetry that gravity is built upon is not entirely perfect? And rather than being an imperfection and a failure of the theory, is actually something new to understand. In fact, in the past 5 years or so, current observations seem to indicate that different physical systems at different scales do seem to be observing something that doesn't satisfy the same level of universality as we would have liked. This is a diagram showing what is called the Hubble tension that you may have heard of. And just in a nutshell, it gives us the estimated relative probability of what the rate of accelerated expansion of the universe is, depending on who you ask in the cosmic history. So if you ask the light of the very beginning of the universe, it will prefer a particular value, whereas if you ask some other elements in the cosmic history of the universe, they prefer a different value. This may just be a systematical fluke. This may be some uncertainties that we, or cosmologists, don't have a full control over. But today, there's fewer than 1 chance in 3 million for this to be just a systematical fluke. Maybe it is, or maybe it is nature's way to tell us that this profound universality that we rely on to build Einstein's theory of general relativity is starting to crack down ever so slightly. Could it be that this symmetry is not entirely perfect? And in that case, gravity, just like the weak force, would switch off at some point. And that would mean that only a small fraction of the vacuum energy will contribute to the accelerated expansion of the universe. And that could potentially be more consistent with the rate we're observing. It's not so much that it will lead to a smaller amount in space, is that we will need to account for less of it in the whole history of our cosmic universe. Now, in fact, the idea that this symmetry could be slightly broken, or that gravity could have a finite range, is a natural idea. We already understand from the Higgs mechanism and from the weak force how this could happen. In practice, all we need to do is to give the same thing to gravity as it was the case for the W and the Z boson of the weak force, is to give them a mass. And that would, in principle, help us taming down the force, the strength of the force. Now, the idea that gravity could have a finite range is not at all a new idea. It's something that Newton himself contemplated, not so much in the framework of particle physics and general relativity, but he himself contemplated the possibility that his universal law of gravitational attraction could have a finite range. And Laplace after him, and even at the beginning of the last century, Pauli, who can be seen as one of the founders of quantum mechanics, first contemplated the possibility at the particle level for the particle of gravity to have a mass. And even Salam contemplated the possibility for gravity to interact with another element which will look like a graviton with a mass. But the possibility has always been refuted, not because it wouldn't be consistent with our observations, In fact, it would be the opposite. Nowadays, it could potentially help us with our current observations. But rather, because breaking the symmetry of gravity always seemed to lead to instabilities which were too high, too large to make sense of. And the whole structure of space-time will literally fall apart. And this is until these two really incredible gentlemen, I'm a bit biased, but they're really incredible, came along. Gregory Gabarazzi and Andrew Tolley, who's at Imperial, and in fact find a way to engineer the internal structure of gravity in such a way that the level of symmetry from the outside is not obvious at all. It may even seem kind of counterintuitive from the outside, but you can engineer the inner structure of the model in such a way that it maintains some balance and the model can be stable. In practice, what it really means is coming up with a slightly new kind of architecture, a little bit like those Penrose stairs, which seems impossible from the outside, but really creates a new space in its own where all of the pathologies are locked on their own side. I'm not going to go much further with the analogy than that. If you want the details, I'm happy to write on the whiteboard. So if the symmetry of gravity could, in principle, be ever so slightly broken, and through the same token, the gravitons could have a mass, the first question we should ask ourselves is what is its value, and is there any signatures? Can it be observed? So in fact, within the realm of particle physics, if the graviton had a mass, it would be the lightest massive particles there is. It would be 30 orders of magnitude lighter than the neutrino, so really, really very light. And so it's going to be really, really, really hard to observe it. But you are engineering really, really incredible devices to observe it. And one of the things one can do is to use gravitational waves as a way to communicate with gravity as it propagates through the whole of the universe. So we know that as two stars or two black holes are accelerating around each other, are merging towards each other, very close to each other, they distort the fabric of space-time so much that they radiate through gravitational waves, a bit like a star radiates through light. But those gravitational waves travel through space for millions of years until reaching us here on Earth, where they disform the space within our instruments, and that's how they are detected. And here on the left, you probably recognize the first signal, gravitational waves signal, direct detection of gravitational waves on Earth in 2015. And so, in fact, from this signal, the first signal of gravitational waves observed, it enabled the community to identify the precise behavior of the different frequencies of gravitational waves. And I'm really sorry here, I can't change that, but the first waves being sent, they're a little bit lower frequency, and the last one in the signal is a bit higher frequency, so the color should be the other way around. It should be red first and then blue first. But the signal being sent is a signal that carries slightly different frequencies. And so by looking at how those different colors of gravitational waves have propagated through the universe and making sure that they all evolve in exactly the same way, we can determine whether the level of symmetry is perfect or not. And from the very first detection of gravitational waves, it has enabled us as a community to put a constraint on the level of symmetry carried by gravity, which is better than any other symmetry that we have in nature, including that of electromagnetism. But those gravitational waves that have been observed, they're very low frequency for everybody in the room, almost. They have the order of Hertz frequency. But from cosmological point of view, this is very high frequency. And so in the future, we're hoping to detect gravitational waves, which are much, much lower frequency, many orders of magnitude lower frequency, that would better enable us to understand how different colors of gravitational waves are propagating through the universe. And if there was a very small breaking of the symmetry, then different frequency of gravitational waves would propagate every so slightly differently, and the signal that we would observe would appear every so slightly more compressed. So in the next decade or so, we are hoping to launch various kinds of observations, including, for instance, here, the LISA space interferometer that should detect gravitational waves at a frequency lower than anything imagined before. We are hoping, thanks to the Simons Observatory, to indirectly detect gravitational waves which span wavelengths almost of the size of the observable universe, and from that, being able to test the nature of gravity with unprecedented accuracy. Whether the symmetry of gravity will be preserved, whether the theory of massive gravity that my collaborators and I came across will survive, this is for time to tell. But for now, I just want to contemplate the fact that just here right now, there's gravitational waves that go through us from the edges of the universe. And those gravitational waves, they carry information about the nature of gravity, about the nature of reality. And so detecting them, understanding them, decoding them, will enable us to better understand how the infinitely small is connected to the infinitely large, even how we connect to the infinitely large, and if tiny quantum fluctuations that fill every pocket of the universe, from here on Earth to the middle of the outer space, can have the most profound effect on the evolution of the universe, dictating the fate of the universe, dictating the fate of everything in it. So just think about that. Thank you.
We have a very short time for a very few questions. So anyone? Okay, right.
Thank you very much. Fascinating talk. One question about the general relativity predicting its own failure. It doesn't contain Planck's constant. There's no quantum phenomenon in general relativity. So isn't the failure a failure of the attempt to connect general relativity with quantum mechanics?
So it doesn't, that's the addition of quantum mechanics. There's absolutely nothing wrong, in fact, to add quantum mechanics to general relativity. That's not really the issue, and we do that on a daily basis, almost. One thing about the very center of the black hole is that they don't need to have an extent. And so what does happen in general relativity per se is the existence of a singularity at the very center of the black hole. So the addition of quantum mechanics tells us that it has to break down before we reach the center. But the fact that there is something with no physical presence that has a singularity and for which we can't stop from reaching it, that is a feature of Einstein's theory of general relativity. I would say it goes better with quantum mechanics because it tells us that we have to stop beforehand.
Yeah, I wonder if you could say something on the timescape theory of the universe, which is that the universe is not universally dense, the same density everywhere, it varies. And if you calculate the path of light from the creation of the universe to today, it does away with the expansion of the universe.
We do account in...
Sorry, the accelerated expansion.
Yeah. So is the question of what is a precise density at the very beginning of the universe, or do we account for the fact that the density of the universe changes as a function of time?
Well, the timescape theory is based on the idea that the universe is not universal. The density of the universe is not the same. It varies from place to place. And as you go through different parts of the universe, the light will get accelerated and decelerated, and that will change its frequency. If you calculate that through...
Yeah, and you know, we can even use that. So we definitely use, not me, you, as human, we use how the light gets redshifted, how it increases energy and loses energy as it goes through different regions of the universe. We can do even better than that. As the universe expands, a photon may go through a denser region in the universe, and so it increases of energy. But then as the universe expands, it tries to come out, and it doesn't lose as much energy as it originally had. And so we can actually build and account for all of those things. That's called the Sachs-Wolf effect and the integrated Sachs-Wolf effect. And it's part, I haven't put it in that card, but it's part of some of the observations that we can have in probing, interrogating the universe. So all of this is perfectly consistent.
May I just thank you for just a wonderful presentation. It's the first time I've heard simply the rationale why a graviton may have mass, and I thought it was beautifully done. My question is, the latest dark energy survey data that tantalizingly maybe suggests that dark energy is changing. We're not at 5 sigma yet or not. Could that provide further insights as to whether gravitons have mass, or would you rather wait until we get to 5 sigma before speculating? Thank you.
So if it was confirmed or whatever, it's going towards the direction of having something non-standard in our understanding of the cosmological paradigm. Whether it's too early or not, I get shouted either way, whatever I say, so let me not commit to anything. But the reality is, it does seem to indicate something slightly different. The interesting thing is, if you're trying to mimic this with a standard cosmological tool, as we do for scalar fields, in fact, there's no simple model that can do the job, and there's in fact no simple model that would ever, no model at all that would ever be stable and be consistent with other things that can do the job. So it's really hinting towards having a much richer structure in how we like to interrogate the current evolution of the universe. And that in itself, I think, is really, really exciting. Whether it does happen, it has happened before, that some of this tension simply disappear. Now this tension in reality has remained a bit longer than many of the others and has become stronger and stronger. But not everybody agrees on what's the right intake on this. The truth is they have very, very precise measurements, and so having something ever so slightly different can affect it a lot.
I want to give the audience on this side have a chance to ask questions. So
yes.
There's one more question. After this, that's it. And wonderful, it's your turn.
Thank you very much. Good evening, professors. Thank you for your very informative lecture. You previously mentioned the great developments which Lisa might give a rise to within studying the fundamentals of our universe, but I am wondering as to what are your thoughts on the developments that atomic interferometry could give rise to?
Yes, so I asked if I could talk for 3 hours, and they didn't let me. But definitely, so we can actually, and in fact at Imperial, there's some of the most amazing development in atomic interferometry, enable us to really test the equivalence principle. That's really what it does to some extent, with incredible accuracy, and so very much go into those directions. And so some of the models that we're exploring, we can use either atomic clocks, or we can think of using the detection of gravitational waves from atomic interferometry to better probe them. So I just picked one up, but there's a wealth of different kind of experiments and observation coming up your way. Yeah.
Okay, the last question.
Thank you. I had a question in regards to the expansion of the universe. If we take it as a model of a balloon, and we put cotton inside the balloon, and then we blow the balloon, we know that it expands and everything inside occupies space. But then if we take the universe as our space, what exactly are we expanding into?
We don't like that question. It's really hard. It's really hard to think, what is it we're expanding into when this is all there is. It's not expanding into anything, it's expanding in itself. There's not such a thing as the edges of the universe and a new room that the universe can fill and take place over. So it's really hard for us. We're not meant to do that, to think about infinities. It's possible the universe is infinite, and there's no limit to it. It's nowhere an edge of it that it can expand onto. But I think it's simpler, at least for me, to think of it as a closed universe, as we had in that bubble sort of balloon picture. And so you shouldn't think of that balloon being a universe which is in another dimension. I mean, this may be the case, but you don't need to think of it like that. That whole surface of the balloon is everything, and there's not such a thing as another dimension that you're looking at. So everything is the universe, and what is happening is simply that space between any 2 points is being stretched.
Thank you.
Okay, right. Well, we could stay here for a long time if I let you ask any more questions, but this is time for me to invite Professor Sir Michelle Doherty to come and give a vote of thanks. Michelle used to be the head of physics for a number of years now. She is head of STFC, and they know each other very well. So.
I'm worried we know each other too well.
No, I won't say anything that will embarrass you much. So Claudia's always a hard act to follow. But I would like to just give a little bit of a history of how we know each other before I move on to the vote of thanks. So we were really fortunate at Imperial and in the physics department in particular when we were able to persuade her to leave the US and join us almost a decade ago now. I was personally very fortunate because she joined my leadership team when I became head of department, and she helped us move through some rather difficult changes in the department, and we're now in a much better place. But I think the thing that struck me most this evening was that Claudia has that very rare skill which most of us yearn for, and that is to do world-class research, but describe it to those of us who know nothing about what she really does in detail. And so after an hour's lecture, we think we understand all about gravity. We certainly know more than we did. But sitting there and listening to her talk about some of the fantastic work that she does, I mean, she's a world-class researcher. Peter Lindsay would have really enjoyed this evening because the mathematical rigor behind what you do, didn't come across this evening because you couldn't describe it to us in an hour.
I can go now if you... I can.
I think the other Peter might not be very happy if I allow you to do that. But I think the fact that we sat and listened to every word that you said, there were 20 more hands that were going up around the room because we just didn't have time to cover everything. So I was enthralled. The room was enthralled. Can I, on behalf of everyone in the room, thank Claudia again for a fantastic lecture this evening.
Okay, this ends today's proceeding for most of you. But those of you who have been invited and have accepted to join us for dinner, you know where to go. I'm not going to tell the others. And if you don't know where to go, come down here and somebody will be here to take you there. And have a good evening.